In the previous episodes, I faced an issue with the planetary gear due to its backdash problem in my application. However, did you know that a single gear set can have 6 different ratios depending on how you connect the input and output? Did you know you can feel the ratio difference by rotating and observing it directly? Hi, welcome to Soul Engineering. I'm David. It's a shame that the planetary gear isn't suitable for my project. However, I can still use it as an educational fidget toy by observing, building, and researching how the mechanism works. This planetary gear has a carrier, an improvement from the last one I shared. In this episode, I'll demonstrate how it operates and explain how planetary gearing can produce 6 ratios. Planetary gearing consists of 4 main components: the sun gear, several planet gears, the carrier, and the ring gear. The carrier attaches the planet gears and operates as a shaft, which makes the shafts on both sides differ. The white shaft connects to the sun gear, while the orange shaft connects to the carrier. The orange pieces are considered as the carrier. You can operate it with one shaft fixed in place like this. Choose either another shaft or the ring gear as input. Although they may appear similar, they have different ratios when spin. There are 3 options for the shafts and the ring gear: the input, output, and fixed components. What is the difference? Well, the choice of input and output affects the ratio. The answer lies in the relationship between the gears. There are 2 relationships to consider: the sun gear to planet gear, and the planet gear to ring gear. The carrier interacts with the planet gear and rotates with the sun and ring gear. In a 2-gear system, the 2 gears must have the same linear velocity when they come into contact. Their teeth will not engage appropriately if the gears do not have the same velocity. The velocity at the point of contact is determined by the radius of the gear and its angular velocity. This means that 2 gears can have different sizes and rotate at different speeds, but they must still have the same linear velocity when they come into contact. Let's examine the relationship between the sun gear and planet gear. In order to observe the relationship, the ring gear needs to be stationary. According to the 2-gear concept, the sun and planet gears have the same velocity at the contact position. However, you will notice that the contact position between the planet and the ring gear does not fulfill this requirement since the ring gear is fixed. As a result, the contact position of the planet gear has no linear velocity. This is where the carrier comes in. When the sun gear is rotated, the carrier also rotates. The rotation of the carrier creates a velocity to balance the planet-ring contact position and keep the velocity at 0. With this conclusion, we can come up with a relationship equation: Vs plus Vp equals Vc, where Vs is the contact point velocity of the sun gear, Vp is the planet gear's velocity, and Vc is the velocity of the carrier. The carrier velocity is the sum of the sun and the planet's velocities, because the radius of the carrier is the largest in this situation. On the other hand, there is a relationship between the planet gear and ring gear, while the sun gear remains stationary. The rotations of the ring gear causes the planet gear and carrier to rotate. The linear velocity at the mating positions of the sun and planet gear is 0, just like the previous concept. The equation for this scenario is Vr equals Vc and Vp. The velocity of the ring gear is equal to the sum of the planet gear and carrier velocity, since the ring gear has the largest radius in the system. To determine the relationship of the planetary gear, we can combine the two equations. We can then convert the angular velocity into the relative ratio of the gearing. It's important to note that all the gear must have the same module to work together in a gear system. This means the radius and the number of the teeth on the gear will be proportional. We can rewrite the equations with the number of the teeth instead of the radius to calculate the relationship between the sun, carrier, and ring gear. With these equations, we can have the angular velocities of the sun, carrier, and ring. We can use these three equations to calculate the gear ratio. In this model, the sun gear has 12 teeth, the planet gear has 18 teeth, and the ring gear has 48 teeth. If the gear ratio is output to input, it will be like this. The minus sign means the rotation will be opposite to the input. As mentioned earlier, one of the two shafts or the ring gear needs to be stationary, and the remaining two will be the input and output. By holding and rotating the two shafts in opposite directions, you can feel the difference in resistance caused by the reduction ratio. Or you can fix one shaft and rotate the other to see the ring gear spin. Different ratios will produce various sensations when you rotate. Here is the questions that you guess. If I place the gear on the table and play like a spinning top, which side will be easier to spin? Why? Leave a comment to share your thoughts. This episode is a reminder about my planetary gear research. If you enjoy project-based videos, you might be interested in my other content. As always, moving forward.